All right, so to start talking about torque, I'm going to go through the note guide that you see in front of you right here, and and talk about that. And then afterwards, we'll draw torque two different ways, and then maybe look at an example problem from the book. All right, so torque is the rotational or angular equivalent of force. You can think about it like when you use a wrench, that you have a force acting about a pivot where you have the nut, say here, and you pivot about that nut and you turn it, and so that it goes either into or out of the board, right? Or if it's attached here, so it either points towards the camera or into the paper. And I'm going to talk about why that is. We're also going to talk about it rotationally speaking and give it a positive sign for counterclockwise and a negative sign for clockwise. So, but what we have is a force. What was a force right here as I push up, acting some distance away from the pivot, which is where my finger is right there, right at the end right here. So as I push right here, it's going to put it's going to turn about this pivot point, and we'll talk about what that force does, what that torque does. So torque is the rotational or angular equivalent of force. And this makes sense because we had angular equivalents for position and velocity and acceleration. So torque is represented by the Greek letter tau, which has a symbol, kind of looks like an uppercase cursive T. Torque is a vector. And we're going to talk about it being clockwise or counterclockwise, but that's not quite true. And vectors don't curve. Vectors only point in straight lines, so it's either going to be into the paper, out of the paper, and we'll explain that by the right-hand rule. So right-hand rule working like this. Once again, if the pivot or the nut is right here and you're turning about it, so you use a force, right? You push up, say, and the distance is this way. The right-hand rule says you point your hand in the direction of R, you curl in the direction of force, and the way your thumb points, which is towards the camera or up, is going to cause it to move out of the page, or that's the direction that the torque points. But before we do that, we're just going to talk about it and refer to a force this direction would be counterclockwise, and we'll refer to that as a positive torque. Okay, so right now we say that clockwise torque, or a clockwise torque, will be negative, right? And that makes sense going along with how we started at in counterclockwise is positive, because if you think before we started with our quadrants, and we labeled these quadrants starting from 3 o'clock, we labeled them 1. I could use Roman numeral, but that's okay. 2, 3, and 4. So we were heading in a counterclockwise direction. And so this is going to be our positive torque when we move in this direction. And when we move in the opposite direction, 4, 3, 2, 1, that's going to be our negative. Our clockwise torque will be negative. So if I had taken that same wrench and pulled down, then it would be a negative torque. And if I use the right-hand rule there, I point my fingers in the direction of R, force is down, so I curl in the direction of F, and now you can see my thumb points into the page or down. Or I should be careful saying down. It's into the page, because down was the way I curled. I curled down, my thumb is pointing into the page. I'll come back to talk about the right-hand rule later in this unit or the next unit. Torque is calculated according to the equation torque equals R cross F. So this is called a cross product, and this is similar to work in that work was F dot D when we had our force and our distance, and it was FD cosine theta, right? So that was one way to multiply vectors, and that was called the dot product or the scalar product, because when you took W equals, if I go back for a second and say when we had work, we multiplied two vectors, and we got FD cosine theta. But our answer, our answer was a scalar, right? This didn't point because work is a scalar. You might say, well, it had a negative or positive sign, but that just meant that energy was gained or lost by the system. It didn't mean anything about the direction. Here we're going to multiply two vectors, but we're going to get a vector product. So we call this a cross product because it's different because now when we multiply two vectors, we get a vector versus before with work and the dot product or the scalar product, we multiply two vectors and we get a scalar. All right. And these are just our vector hats. It just indicates that those are vectors. Okay, so let's define what R and F are. R is the distance from the axis of rotation, also referred to as the pivot. It's measured in units of meters, so axis of rotation is also called the pivot. And it's real important that you know where the axis of rotation is because you have torque about a point. You have to turn about a point, and where that axis is matters. If the axis changes, then the problem changes, so you have to know where that is. The force is just a push or a pull, just like we learned before with forces. Units are newtons, and here, because we're multiplying then R and F, right? Really, we're going to end up with units of Newton meters. We're taking a force and multiplying it by a distance, but it's not that simple, right? Just like work was F dot D. Here, R cross F, which is different than F cross R, so we have to be careful about the order we say it in. R cross F is really going to turn into RF sine theta. So that's, or phi. We can use a different Greek letter here, or phi or phi, or however you say it. It's fine, you can say it either way. And so here's our equation for torque then. Torque equals the magnitude of the distance times the magnitude of the force times sine phi. We don't attach a sign to it because the sign, positive or negative, comes from whether it's clockwise or counterclockwise. And we'll attach the sign there based on that. So anyways, phi is the Greek letter right here, like a zero. It looks like a zero with a line through it, or a circle with a line through it, kind of tilted slightly. Phi is measured from the radial line to the direction of the force. The radial line is what happens when you take the radius and or the distance, right? The distance away from the pivot, which is R. It's not technically the radius, I guess, but it kind of is because it's kind of like it's moving in a circle, it's rotating. But anyways, it's just when you take that distance and you just extend it out. So we'll have that concept a couple times with the force. If we take our force and we extend it out, we can create a force line or a line of action, and we can do the same thing with the distance r and extend that out and get the radial line. So an example of the radial line would be right here. We just dotted line. Here's r right here. Notice it's pointing away from the pivot, and the radial line just extends out. And this angle the radial line makes with F is known as phi, or phi. The force line, or the line of action, would be if I took this force vector and extended it back. All right, so here's another example, slightly tilted, but you can see that you have the radial line extending out from R, and phi being created between the force. The force is applied at the end of the wrench, and you have phi being right here. So you notice that, and this is probably like one of the most important ideas, is that if you used a wrench, you would use it like this, right? You would push right here where my hand is, right? And you'd push up, or you'd push 90 degrees. You can still turn the nut, or when you push like this, right, at an angle, but it's not as productive. It's not going to accomplish as much torque. So this chapter is all about accomplishing torque by when the force is at a 90-degree angle to the distance. So meaning that that's where we produce the most torque. And that kind of makes sense with our definition here, because we see that torque is RF sine phi. Well, sine, when is it at a maximum? Sine 0 is 0, but we know that sine 90, or pi over 2, sine of 90 is equal to 1. So thinking, about how the sine and cosine function look on a graph, that would be the maximum. So when you have 90 degrees here, you accomplish maximum torque. So in a case like this, where your angle isn't at 90, then only the perpendicular part of the force accomplishes torque. So we would want to find this perpendicular component right here. If I was to dotted line it in, this would be F perp, and really the torque is going to equal F perp times R, because that's really what we're working with here, right? And that's really what's important. Sometimes you might use sine or cosine to solve a problem. Sine makes more sense because the sine of 90 is 1, but sometimes if you're given an angle which isn't phi, maybe it's an angle that's some other angle, you might end up using cosine. So because torque is equal to R times F perp, or torque is equal to R perp times F, and they're both torque, so they're both correct. And so really that's what you're doing. So if you're ever confused because you see a cosine popping up or something, just remember that this is true, that torque happens when the two are perpendicular to each other. So you're just trying to find when they're perpendicular, do the multiplication, and that's it. And that's all you're doing. So anyways, coming back to here, we see that if we solve for F perp, because it's opposite, right, this angle phi, that it would equal, since it's opposite, would equal the hip sine phi. So we can see where this equation comes from, then that torque is equal to R times F perp, which is the same as the hypotenuse F times the sine of phi. So you can see where these equations are coming from and why they make sense. But once again, if I'd given you a different angle, like say I'd given you this angle up here, let me see if I can draw that in. Right, this angle up in the corner. If I'd given you that angle, then obviously, and phi was still here, and maybe this angle right here was theta up in the top corner, then you would have to take the cosine of theta to get this F perp, right? Because this angle is adjacent to this side, right? Or this side is adjacent to the angle. So, yes, you have to be careful based on what angle you get. You always want when F and R are perpendicular, though. All right, so here's another example. Radial line drawn in. Once again, this angle is the angle we're using right here. F is now pointed this direction, so this is going to be this is going to turn clockwise, so we're expecting to see a negative torque here. So then you run into the instance where you have your force, maybe right here, maybe you come up to the wrench and you decide that you are going to pull on the wrench this way. And how much would that turn the nut right here? And the answer should be not at all, right? 0. Because you can think of it this way, the angle between F and the radial line is what? 0. So if that's 0, then you're taking sine 0, and sine 0 is 0. Same is true if F is over here. Then this angle, you can think of it as being 180 if you like. And sine of 180 is 0 as well. But what we're seeing is that when the force is directed through the pivot, that we produce 0 torque. The force is directed through the pivot. And that's going to come up in the next part lecture as well, that when you have a force directed through the hinge or the pivot or the axis of rotation, you're not going to produce any turning force, which makes sense, right? If you came up to this wrench and started pushing this way against the nut here, it wouldn't turn it. And so you wouldn't bring it out of the board or into the board if it was say a screw or something or whatever you're trying to turn there. Okay, so the bolt. All right, so torque is at a maximum when phi is equal to 90 and the sine 90 is equal to 1. So how can we make torque? So I guess this is important too. Torque is at a maximum when R and F are perpendicular, and that's really the key point of the lesson. I already went over that. But you can see that to make your torque the largest, you could get a wrench here that's longer. You could push with a greater force, and then you make sure that this angle is 90. So it would not be as, if I was pushing this direction right here, this would not be at 90 degrees to R. So it'd be more efficient for me to push straight up like this. All right. And you might say, well, wouldn't that change? I guess, if you push straight up and now the wrench was here and you push straight up, well, now that's not 90, right? So what I'm saying is if the wrench goes here, right, 90 degrees is no longer to R is no longer straight up, right? Now it would be here. So you would always want to push at a 90-degree angle to your wrench, or pull, or vice versa, whichever. All right. So so a question here: how might you push on a door to generate zero torque? Well, you'd push through the pivot or hinge. So you might push on the end of the door towards the pivot, or pull on the door, and it wouldn't cause the door to turn, which should make sense. Why isn't the door handle placed next to the hinge? Well, then you would have zero distance away from the pivot, right? R would be 0, and well, it wouldn't technically be 0. It would be really small, and it would decrease the torque, right? So I guess it would be 0 if it was at the hinge, but if you put your door handle right next to the hinge, it'd be really hard to turn, and so they put the door handle far away from the hinge, which should make sense. Check the next time you use a door. And then finally it says, if I'm pulling a door shut, what is the best angle of phi to generate torque? And we would just say 90, right? So assuming that you're going to pull here to shut the door, you want to make sure that your force is directed at 90 degrees to the radial line or to the door itself, and that would cause the most torque on the door. So the most important thing to understand, like I said, is that R and F have to be perpendicular to each other to generate torque. And a lot of times students just memorize torque equals RF sine phi, but it doesn't mean that they understand what's happening. So let's look at a couple examples of how we might draw torque. So let me go ahead and sketch a wrench, and you should do the same. I'm just gonna trace this one I have. Okay, so let's say you take a wrench and you have a nut right here that you're gonna turn. And you're going to hold the wrench maybe right here. So you're going to put a force, and let's say you decide to work at some other angle than 90 degrees, that you try to push the wrench like this. And we can see that this force is some distance away from the nut here, which is the pivot or the axis of rotation. Also call it the pivot. And so let's go ahead and draw R in. Now remember, R is also a vector, so it points. And so what we can see here then is if this is R, then our radial line is if we follow R out further. And this creates an angle right here. And this angle is equal to phi. So make sure you're drawing all this down if you haven't been. So we're good so far, but we learned that this formula, what it's really trying to tell you is that torque is equal to R times F perpendicular, right? And so we need to know where the force is perpendicular to R, or the radial line here. So I better write that down, that this is the radial line. And you can see, well, if you remember what we did to split vectors into components, right? We'll just split this force into components. We'll say a piece of this force points this way, maybe F of X, and a piece of this force points this way. We'll say F of Y, but we don't really care about calling it, this is 90 degrees, Fx and Fy, right? What we're more interested in is which one of these Fx or Fy is perpendicular. And I guess I can label them Fx and Fy if it makes you happy. But which one of these is at a 90-degree angle to the radial line? And so it's obviously Fy, right? Fx would be parallel to the radial line. So because that's true, then we can say that Fy is also known as F perpendicular. And so down here, you can see now that F perpendicular is this side right here, which in my right triangle, this is a right triangle, across from 90 is my hypotenuse, and across from phi, is my opposite, and next to phi is my adjacent, but Fx doesn't really matter here, but it is the adjacent. You can see then that if I want to know what F perp is the opposite. So I need a formula for opposite, right? And we said before that sine of, we'll say phi, I could have said theta, is equal to the op over the hip, right? And therefore, if we want to know what the opposite is, we just need to rearrange this to be op is equal to multiply both sides by hip sine phi. And we can take that a step further because we know that the opposite then is also equal to, the hip is F sine phi. So I come down here, torque is equal to R times F perp, and F perp is the opposite, right? So F perp, I guess I probably should have put that in, plugged that in right there. My fault. F perp is equal to F sine phi. And so, if I rewrite it one more time, now it makes sense why where the formula torque equals RF sine phi comes from. So this is once again more important to understand than just memorizing this. This doesn't do you any good in this chapter. You have to understand that you're all about R and F being perpendicular. So you need to find either the perpendicular part of F or the perpendicular part of R when the two are not perpendicular. If I could have, if I would have just pushed straight up with a force directed this way, it would have been much easier, and I could have just said torque is R times F times the sine of 90. But it gets more difficult, as you can see, when the force is, say, at this direction, or some other direction, or this direction, and it gets more challenging, right? So this is why you can't just memorize this formula. All right, let's look at this, a second case of drawing torque. So I would consider this to be case 1, right? And that is where you find the perpendicular component of F. All right, let's look at a case 2 then. Let's use the same. Let's do everything exactly the same, right? So I'm going to go ahead and draw my wrench. You should do the same. I'm just drawing it horizontal. Nothing fancy with the wrench. Oops. Okay. And we're going to keep it just the same as last time. So I think our F value is roughly here, right? And we had our nut being here. And F kind of pointed, say, like this. Sure. My angle probably isn't exactly the same, but it's close. And we said that this distance right here from the pivot to the point where the force is applied is called R. And we said also that if I was to extend this out, this angle is phi. All right, so now instead of solving for the perpendicular part of F, what if we look for the perpendicular part of R? Because sometimes this is going to make more sense to do. So what we're going to do is take, and this was called the radial line, just so we're clear. What if we take F and extend it back? So the F's pointed this way. So if I had a straight edge, maybe I can use this wrench. I'm just going to extend this back. How far? I don't know, however far you want, but take up a decent part of the page there. And what you can see then by looking at this is that this new dotted line is also going to get a name. We're going to call it the line of action. It's also referred to as the force line. And what we're going to do to find where R is perpendicular to this is now we're going to look for a piece of R. And the trick to finding this component of R that's perpendicular to the force line, which is with this piece of R that's perpendicular, is going to be called R perp. The trick to finding it is you find your pivot and then you start looking at distances. Like if I took my pivot and just drew a straight line from the pivot through the force line, where is this line the shortest? So right here it's longer, and if I move this way it's shorter, and if I move this way it's shorter. So I'm talking about this distance from my finger or from the pivot to where the force line is. So where is the shortest distance? Right here or here, right? This distance right here is clearly shorter than this distance up here. You see what I'm saying? So the shortest distance between the pivot and the line of action is a component of R, right? This is like if we were splitting R into components. This is perpendicular to, sorry for the drawing, looks like my line's a little crooked. Oh, Lord. That's a straight line. All right. I don't know what to tell you. Okay. So anyways, this shortest line here, right? I can't really fix it with the marker. I can try to fix it. Let me see if I can draw it a little bit better. Right? I'll get rid of this. Okay. So that short line right there, that creates a right triangle. Ignore that mess. Right triangle right there. And what you should notice is that this dotted line is referred to as the moment arm. Now, you don't have to remember that, really. I don't think we call it a moment arm a ton in class, but what you need to know is that because the 90-degree angle is here, this R then of this triangle is the hypotenuse, right? And so we have a right triangle, and this is our perpendicular, the moment arm. It's a part of this right triangle. Now, what part is it? Well, it depends where phi is. Well, if you think about phi, say this angle here is 60, and if I go extend this all the way to here, this would be 120 over here, right? So down here, this is like the flip of that. This would be 120, and this would be 60. So my point I'm trying to make here is that this angle right here is also phi. All right, you should be able to see that because of the way the geometry works there. If you can't see that, then pause it and look at that a little closer. Convince yourself that these two angles are the same. All right, so this is phi. And so what we said is that torque is what happens when you take the perpendicular component of R and multiply by F, right? So we said that torque is F perp times R, but it's also R perp times F. And what the heck is R perp? Well, if we go and look at our right triangle here, here's our angle, here's our hypotenuse, here's our 90-degree angle. That means that R perp is across from phi, so that would make it an opposite. So my point is that when you multiply your force, maybe it's 100 newtons, by R perp, whatever this distance is right here, that this distance is equal to, it's an opposite, right? So if I use my formula just like I did last time, if I come down here, sine phi is equal to op over hip. And if that's true, then we can go ahead and rearrange and say the opposite, which is what we're interested in, is equal to the hip sine phi. And the op then, which is also, in this case, known as what? R perp. And the hip is known as R. I can then sub those in down here. That, let me see if I can show you this. R perp is equal to R sine phi, right? Okay, so taking this then and subbing it in up here, we can see that torque is equal to R sine phi times F, right? And I can rearrange that and rewrite it one more time. Torque is equal to F times R sine phi. And that should look really familiar, right? Because check it out, right? We use another triangle, another drawing to make sense of torque. And once again, this equation came up, right? That we can get torque equal to RF sine phi or FR sine phi. And either way, it's true. But just be careful, right? Because had they have given us this angle over here instead, right? I don't know why they would do that, but if they did give us this angle, then we would have had, this would have been an adjacent, and I would have used a cosine formula. So this is so that's why it's the most important thing is to understand that torque happens when F and R are perpendicular. That you can push at this weird angle, but the only torque you're doing is when the two are 90 degrees to each other. So the formula simplifies into this. And that's kind of the big idea. Had you used your force in this direction straight up, then this angle phi would have been 90 degrees to the radial line, and you wouldn't have wasted any of this force. So it is less efficient to push like this, because only the perpendicular part of the force, or the perpendicular part of R, is doing torque. So once again, you got two ways to figure it out, two ways to draw it. Which one should you use? You use the way that's more convenient. But it does you no good to memorize this. You should instead practice drawing your moment arm, your line of action, and finding R perp, which is the moment arm, or draw your radial line and find F perp. You might say, well, this way is a lot easier. It is, but sometimes this way is more useful. Sorry for the scribble mark. This way is more useful because you know more about maybe you're given maybe you're given a force at a weird, it's pointed in a weird direction, so it's easier to do this. Maybe you were pulling this direction, right? So it's easier to work down here and make sense of the problem. So yeah, so that's the idea. So we'll do a couple more examples and then we'll call it good. All right, so let's say we have a door that looks like this, and its hinge is right here, and this is a top view of the door, and we'll say that the distance from we'll say a force is gonna be directed like this, and we'll call this F, and we'll say that this distance right here then is R. You can go ahead and draw this as well. And they tell us in the problem that a 240 Newton force is used to open this door, and that this force is directed at an angle of 20 degrees from the vertical, or not from the vertical, but from perpendicular. So that this angle right here is 20 degrees. But we have to remember what we learned before, right? That this is called the radial line. Oops. And this angle, if that's 20, what does this angle have to be? Well, it's got a total 90, so this has to be 70. And that angle is phi, right? So that this 70-degree angle right here is phi. So the reason I bring this up is because we learned a second ago that torque is equal to R times F perp, and F perp is where? Well, if we look at this, we can go ahead and draw a component here. We can take another component right here of F, and we know that this is F of X and this is F of Y, but we know that this is perpendicular to R. So this side would be F perp. So the reason I'm bringing this up, if I redraw this down here, just really quick, this is F. This is 90 degrees. And this is phi. We can see that F perp is an opposite. And we can see that F is a hypotenuse. So my point is, we can then use, we know we want to solve for this opposite because we know that torque is equal to R times F perp. and we want to know what torque or how much torque is happening here. I think they tell us that the R value is 0.75 meters, or 3/4 of a meter, or yeah, 75 centimeters. So 0.75 meters, almost a full meter stick. And so what I'm trying to say here is then we want to know what F perp is. If we know F perp, we can solve. F perp is an opposite. So our formula is sine phi equals op over hip. We're going to solve for the opposite, so the op has to equal hip sine phi. And that's the same as saying F perp, which is the opposite, is equal to F sine of 70. So coming up here, we can say then torque is equal to RF sine 70. R is equal to 0.75. Whoops, 0.5. Let me you can just 0.75 meters times 240 newtons times sine of 70. It's getting hard to see. Hopefully that's clear. 0.75 meters times 240 newtons times sine 70. If we go ahead and plug that in our calculator, let's see here. It should be in degrees. Looks like I am, so that's good. 0.75 times 240 times sine 70 is equal to 169.145 or 14. So 169.14. We're going to go ahead and call that Newton meters, and we'll be good. All right. So in the textbook on page 200, this is similar to the problem they have, right? Except in the textbook on page 200, they have the same drawing, which I should probably do a little lower so I have enough room. Go ahead and draw it down here. We're going to go ahead and put the pivot right here once again, or the hinge. This force is going to be directed like this. It's 240 newtons, and that will be F. And from perpendicular, and we know that this angle right here is 20 degrees. And I'm going to go ahead and call this angle theta. All right. So the idea here being that I can then draw R in. This is going to be 0.75 meters. And coming back over here, we can go ahead and draw our components, right? Where this is one part of F, and this is the other part of F. And once again, I want the perpendicular part. So which one's perpendicular to R? We would say this one right here, right? This is 90 degrees right here. So I'm going to go ahead and draw in F perp, and then look at my triangle here, right? I have the full force F, so this has to be the hypotenuse, because it's the largest part of F, right? F perp is 90 degrees to this, but up here in this triangle, it is not the hypotenuse, or it is not the hypotenuse, right? It's a piece of the hypotenuse. So my 90-degree angle for this triangle is right here. So that's tricky, right? Because I'm going to use that 90-degree angle to solve this. But the reason why I call this, it's really f of y, right? The reason why I call f of y f perp is because this dotted line f of y is perpendicular, right? That this is 90 degrees right here to r. All right, so there's two things going on there, so that's kind of confusing. Anyways, we want to know what f perp is because we know that torque is equal to r times f perp. Coming up to this problem, we see that the 90-degree angle is here. This force is split into an Fy and Fx. Fy is adjacent, right, to this 20 degrees. So I'm going to call this side the adjacent. And you can see what's going to happen because I'm using 20 degrees now, and this is the adjacent, that's going to change the formula, right? I have a hypotenuse. I want to know the adjacent, so I'm going to grab my cosine formula. Rearrange. And then go ahead and plug some values in. So f perp is equal to the hypotenuse, which is f times the cosine of 20 degrees. So I can go ahead and sub that into there. All right, and it just so happens that this is a neat thing to know about math, is that we're going to get the same answer as before, right? Because the sine of 70, well, the cosine of its complement is the same thing, right? So that's kind of what we're saying here. And so we can see that, I can even type it in, right? The sine of 70 is the same as the cosine of 20. And we see the two numbers coming up there on the calculator. So, so anyways, I'm going to take cosine 20, multiply here by torque is R 0.75 meters, 240 newtons, times the cosine of 20 degrees. And because this is the same as the sine 70, when I type it in my calculator, I'm going to once again get 169.14 Newton meters. And I can go ahead and do it just to prove it. So I already have cosine 20 in there. Just hit answer multiplied by 0.75 times 240. And I get 169.14 Newton meters. This is also going to be a positive torque in both cases because this door is going to, this is a counterclockwise torque. So it is right to keep it as a positive sign. But there you go. So this is the way they explain it in the book. But I know students are always confused because they're like, what the heck? I thought it was torque equals RF sine phi, and then all of a sudden they're using cosine, and the book really doesn't explain why. But you can see it was just an unfortunate part of the problem because they just gave you a different angle. We're used to getting the angle between the radial line, which is right here, and the force. We're used to getting this angle, which is 70. Had you used 70, then you can use sine phi, just like normal. All right. Hopefully that makes a little bit of sense there. So then an example 7.10. And this is on page 201. They take the wrench and they start it off pointed differently, right? So the wrench is going to point, excuse me, like this, and the nut will be here, and this is also known as the pivot, right, or axis of rotation. But this time the force is going to be directed straight down. And they tell us that this distance right here to the force where it's applied is r. And in this problem, they tell us that the wrench is angled at 30 degrees above the horizontal. So then they say calculate torque using two methods. And so I think the easiest one here to use, you got to ask yourself, is it defined F perp or is it defined R perp? We know one more thing. We know the wrench, I don't want to forget this, is equal to 20 centimeters, I believe. Yeah, so R is 20 centimeters. We don't like centimeters, so that should be 0.2 meters. And so the easiest one to use here is actually going to be defined R perp, right? Because we said that if you extend F out this way or this way, that this is called the line of action or the force line. And so if you find the shortest distance between the pivot and the force line, that is this right here, which just so happens to be the horizontal, right? This is R perp. And this, because R perp is perpendicular to the line of action. And it just so happens that that is going to allow us to find R perp, which is the part of R, right? It's a component. Sorry, I was interrupted by a phone call there. So this is the component of R that we're interested in. And so what I'm trying to say then is that R perp is going to be adjacent to 30 degrees, right? Because this is going to be my hypotenuse up here. And this is going to be my adjacent side. So once again, we don't get to use sine, right? Because they stuck us with this odd angle. Now, if we use 60 degrees, we could get away with using sine. But they gave us 30, and it makes sense to use 30, so I'm just going to stick with it, right? I want to know what the adjacent is, so I'm going to go ahead and write out my cosine formula. Cosine of, we can call this phi or we can call it theta. It doesn't really matter. I'm going to call it, what does the book do here? I don't know if they call it anything. It doesn't really matter. It's just a Greek letter. It's a variable. I'm going to stick with what I did before and call it phi. So I'm going to get rid of that. Okay. So, or I'm sorry, I call it theta. And so this is my theta here. So anyways, we have cosine theta equals adjacent over hip. Rearrange to solve for adjacent. Plug in what we want here. This is R perp. The hypotenuse is R times the cosine of theta. So what I'm saying then is the torque is equal to R perp times F, right? Plug this in for R perp. So this right here can go right there. Okay, and then we can go ahead and plug in our variables for that. So we have torque equals 0.2 meters times the cosine of 30 times F, which I think they tell us for this problem is 100 newtons. They have to give that to us. So we do the multiplication there, and cosine of 30 is like 0.866, so I am going to need my calculator here, or square root of 3 over 2, right? So we get 0.2 times 100, which is just 20, times cosine of 30, which is equal to 17.32 Newton meters. Now I have to be careful here because this is directed clockwise, so we're going to go ahead and put a negative sign on there for our clockwise, or you could clockwise torque, or you could say 17.32 Newton meters clockwise, right? And that would work too. But you have to indicate direction because it is a vector. All right, and that's about it. So I think the problem said to do it two ways. The other way would be to find f-perp. Let's see if I can get a, maybe I can just draw it on here. Maybe I can do this. So right here is the perpendicular part of this vector, right? So I'm saying if this is, when we find f-perp, this is r, and this is the radial line. If I extend this out, and f-perp should be 90 degrees to the radial line, right? So this right here, this piece of f is f-perp. And this piece of f doesn't matter, but you can see by doing this, I'm building a right triangle, right? Here's one part of f, here's the other part of f. You might say, oh, this is more confusing. Yeah, I think it is slightly more confusing. I probably wouldn't use this method here, but let's look at it, right? And this is 60 degrees. And so therefore this angle right here is 30. And the reason I bring this up is because you can see that f-perp, even when you draw it out this way, is still adjacent to the 30, right? So you're going to end up using cosine here to find f-perp, right? Because what I'm saying, my battery's running low on my phone, so I'm going to try and get this in. Torque is equal to r f-perp, and then torque is equal to r and f-perp. Since f-perp is adjacent, the adjacent is equal to the hip, right? Well, what's the hip here? Here's 90. Across from 90 is f, so it's equal to the hip cosine of theta, right? And so we can go ahead and plug in our values then. R is 0.2 meters, F is equal to 100 newtons, and you have it times the cosine of 30. And so you can see that even though I use this alternative method, that this still is the same as this, and it's still pointed, it's still going to be a clockwise torque, so it's still going to be negative. So our answer here will be torque equals negative 17.32 Newton meters, or 17.32 Newton meters clockwise. So it doesn't matter which method you use, although the first one's much easier, and don't think about sine and cosine as much as just trying to find where r and f are perpendicular, where one is perpendicular to the other. So looking for f-perp or r-perp, and multiply. If you go r-perp, multiply by f. If you go f-perp, then multiply by r. And and then solving for the torque. And that's it, because torque happens when the two are perpendicular. All right, I think that's about it. And yep. So I also just wanted to take a look at example 7.11. And in this problem, I just thought it was kind of neat because you had the axis of rotation right here, and you had two forces on the axis of rotation, right? This force was at a distance r away, and it was the weight of the anchor, which is directed this direction, and they called it the tension. So there was a rope tied here to the capstan, right? And is the idea that in it's a device used to pull the anchor up, and they had one of the levers that you could use to do this was directed outward, and we'll say like right here, and this was a distance away from the axis of rotation that was equal to 7 times r, and the force applied out here was less. And the problem says that the torques generated here are equal, right? And so you have one force that might be greater but is applied a shorter distance away, equal to a smaller force which is applied a larger distance away, is still accomplishing the same torque. So with much less force, because you have this long distance here away, right? And so in both cases, even though this force is directed this way and this force is directed this way, both are at 90 degrees to the distance from the axis of rotation, right? Here's a 90-degree angle right here, and right here, even though this one's directed this way, it's still, compared to r, it's r, which is 7r, compared to 7r, it is at a 90-degree angle. So this is doing 100% torque, and this is doing 100% torque. But they tell us that the torques have to balance. So there's no net torque. So because of that, we were able to say that the sum of the torques has to equal 0. So we're going to add the torque from F and the torque from T. And so you might be able to write it, well, torque from T is going to be, well, it's going to cause this capstan to turn counterclockwise, right? So this is going to be a positive torque, and the torque from F is going to turn it clockwise, which is going to be a negative torque. So when we add these up, so I'm saying you have the torque of T being positive, and you're going to sum them. You're going to add it to the torque of F, which is going to be negative. So it's going to be a negative torque from that force is equal to 0. So let's go ahead and plug in our values, right? So we know the torque from T is going to equal F, or RF, R cross F, which is going to be R times T, and then the angle is 90, so sine 90. So we're able to say, let me see if I think I can write this down here. I think I have enough room. R times the tension times the sine of 90 degrees, or phi. And we're going to go ahead and subtract that from this R value, which is 7R, times F times the sine of 90. And that's going to equal 0. So we can go ahead and solve this equation. So right away, by looking at this, we know sine 90 is equal to 1. So I'm going to rewrite it more simply. RT minus 7RF equals 0. We can go ahead and cancel off the r's. Just factor an r out, divide both sides by r. It goes away. And we're left with T minus 7F is equal to 0. And I think the point of the problem is to solve for F, so I'm going to kick 7F over to the other side. So we get T equals 7F, and we can see that F then is equal to T over 7. So you might have this heavy anchor, but because the capstan has this long lever, you're able to push with a much smaller force, right? The anchor's weight or the tension divided by 7 to pull the anchor up. So that's pretty neat. And this is a way to get mechanical advantage, right? This is a machine here, a simple machine that allows you to push with much less force because you're pushing so much further away from the pivot point than what the anchor is. And yeah, so it works out, and it's a good thing. So that's the last example.